Hello, I'm going to continue with section 7.3 in STA 2023 statistical methods. So we did two examples in the previous video. Now we're going to do two more. The more examples we do, the better we'll get at it. So this example says, Samuel Morse suggested in the 19th century that the letter T made up 9% of the English language. Assume this is still correct. A random sample of 1,000 letters is taken from a randomly selected large book and the T's are counted. What is the approximate probability that the proportion in our sample will be between 7% and 13%? Now that we're getting a little better at this, let's make sure we truly understand the problem. What this is saying is the population is all letters in the book, and 9% of all letters are the letter T. So the population mean is supposed to be 9%. We're wondering if I take a random sample of 1,000 letters, what's the probability, the chance, that my final result will be between 7 and 13%? So before we even get started, do you think this is going to be likely or not very likely? If it's supposed to be 9%, what would be the chance of getting between 7 and 13? I think it's going to be very likely because 9 falls between what we're looking for. Now the chance of getting between 50 and 60 would be very unlikely, knowing that it's only supposed to be 9%. So that's the thinking I want you to have at this level. So we check our conditions. So number 1, was it random? Yes, it's stated. Number 2 is the population, all letters in the book, greater than 10 times the sample size. 10 times 1,000 is 10,000. Now I don't know how many letters in the book, but this is how many letters, not even how many words. There are more than 10,000 letters in a very large book, let's say. Then n times p, which is 1,000 times 0.09 is 90, that's greater than 10. And n times 1 minus p, which gives us 910, is greater than or equal to 10. Then we're going to find our standard error. And again, this is a place I want you to be very careful because this is where mistakes happen. So we take the square root of p, 0.09, times 1 minus p, 0.09, divided by n, which is 1,000. Practice this in your calculator because you should get 0.009. Be careful that there's 2 zeros. Okay? Then we find our z-score. But because we're looking for between two values, we're going to have two z-scores. So we do 0.07 minus 0.09. Do that first, or in parentheses, divided by 0.009, we get negative 2.22. And we have 0.13 minus 0.09 divided by 0.009, which gives us 4.44. Okay? When we do this in the table, negative 2.22 you can find is going to be 0.0132, and that's to the left. Remember, we're looking for the area in between. 4.44 is off the charts. Anytime it's off the charts, we can estimate it to be 0.9999. It could be 9999999 or 10 nines or 100 nines, depending on what the number is. But we'll say if it's off the chart, we'll just estimate it as 9999. And again, the table always tells us to the left, the table always tells us to the left. We're looking for what's between, so we're subtracting 99.99% minus 1.32%, and we get 98.67%. But again, we're focusing on what this number means, The statement is, there is a 98.67% chance of randomly selecting 1,000 letters in which between 7% and 13% are the letter T's. Now, we shouldn't be surprised by this answer because the population mean, population proportion, is 9%. So the chance of getting between 7 and 13 is very likely. How likely? 98.67%. Okay, let's try another one. Okay, this example says, in a hotly contested U.S. election, two candidates from president, Democrat and Republican, are running neck and neck. Each candidate has 50% of the vote. Suppose a random sample of 1,000 voters are asked whether they will vote for the Republican candidate. So we're assuming that each candidate will get 50%. There's your 50%. To determine the standard error, it's that formula again, square root 0.50 times 1 minus 0.50 divided by 1,000, which is 0.016. We have to check our conditions. Yes, it's random. The population is all voters. 10 times 1,000 is 10,000. N times p, 1,000 times 0.50 is 500. N times 1 minus p is 500. Both pass. Everything passes, so we're good. This is a new section that's actually giving us a little preview of the future. If I want it to be within two standard deviations, which is 95%, what would that look like? Well, we have this formula here, which is new for us, and we'll really get into it next section. But to give you a little preview, if I want to find out what would be within two standard deviations, 95%, we use this formula, P, 0.50, plus or minus within both sides, 2, because we're going two standard deviations, 95%, your SE. So if I did 0.50 plus or minus 2 times 0.016, you get 0.032, subtract it, add it, we would say that it would be between 46.8% and 53.2%. Now again, we'll do this in detail next section, but this gives you a little preview. Okay, one more example for this section. So Samuel Morse, the inventor of Morse code, claimed that the most used letter in the English language was E with a proportion of 12%. We took a random sample with a replacement of a modern-day book of 876 letters, and 118 of them were E's. That's 13.47. Find the probability that if we take another random sample of 876 letters, the same proportion would be greater than or equal to 0.1347. Assume that the true proportion of E's in the proportion is, as Morse claimed, 12%. So, like we've done before, P is 12%. P hat, 118 divided by 876 gives us that 13.47%. We're doing a sample of 876, and our population is all letters in the book. Again, it's supposed to be 12%. What's the chance that it's greater than 13? So this is not going to be as likely. It's close, but it's 13 or greater, so it doesn't include the 12, so the chance of this happening is not going to be as high, like in the last example of 98%. So we check our conditions. Yes, it's SRS, it's stated, it's random. Population, all letters in the book, assuming it's a large book, is greater than 10 times 876, which is 8,760. N times P, 876 times 0.12, which is 105.12. 876 times 1 minus 0.12, which is 770.88, greater than 10, everything passes. To find your SE, it's 0.12, 1 minus 0.12 divided by 876, gives us 0.011. Again, I say it every time, be careful in this step. It's where a lot of people have errors. Then we're just doing greater than this time, so we do our P hat, 0.1347 minus 0.12 divided by 0.011 is 1.34. 1.34 would be about here. We're looking for greater than. When we go to the table tells us less than. We get 0.9099, but that's less than. We want more than. 100 minus 90.99 gives us 9.01%. Again, it's not that high because we're looking for greater than 13.47% when it's supposed to be 12. So it's not that high, but it's not that low either because it's relatively close. So there is a 9.01% chance of randomly selecting 876 letters in which 13.47 or more are the letter E. Okay, thank you.